Hello and welcome to this demo of the ground source heat pump screening tool. Before I dive into the demo, I'll quickly show you some of the guidance documents that are available from the homepage. The first of which is this quick start guide. The quick start guide will give you an introduction to the tool, as well as detailed information about each of the input fields that you'll need to be filling in during the process of using the tool. And finally, explainers about what you're seeing in the results page. Secondly, we have the tool guidance. This is a much more detailed guide. Includes some of the things from the quick start guide, but also broader considerations for designing a ground source heat system. So for instance, from step 4 onwards, we have considerations for alternative ground source heat options, increasing the efficiency of your system, so looking at combining heating and cooling loads, looking at shared ground arrays, thermal storage, and then what you might need to do to take your project further. So back to the home page and let's get started with using the tool. The first thing you'll see are these two options. If you're new to the tool, you'll always be using this top option, but you do have the ability to return to your previous results and also to edit previous inputs with a passcode. I'll come to this section at the end. So for now, let's continue as if we're new to the tool. First is the site name. This can be anything and is just used for your own reference for later. For example, if you downloaded the results, you can identify your project by this name. Next, we input data about the location of the site and about the area we have available for closed loop boreholes. This is very easy to do, so you can start by either searching for your postcode, and when you search for the postcode, you'll be taken to that location, or you can just use the map to pan around directly and zoom in. In this case, I'm looking at a primary school here. So the first thing we need to do, and it's outlined here in this help text, but the first thing we need to do is add a pin to the map where we would like the sort of center of the area of the boreholes to be. This location is important because behind the scenes, the tool has lots of geology data across England and hopefully in the future Scotland and Wales, which tells us how much heat can be extracted from the ground across different locations. So the location provided should be the location or the center of the location where you want to install the boreholes. Once you've added it to the map, which I just did by clicking this marker tool and clicking on the map, you can also move it around, or you can delete it with this icon and place another pin on the map. Next, we have the option of importing the land area that we have available for closed loop boreholes. This is an optional input, so actually at this stage we could go straight to the next step. If you do go to the next step without inputting the land you have available, then the tool will calculate, given the heat demands for the site, which we input on the next set of pages, it will calculate how much land area is required to meet the full heat demand for the site. Another way of using the tool is to input the land available, however, and we can do this in a couple of ways. So we can use the polygon tool on the map here. If I do that, then I can start outlining the area that I wish to be considered. So typically we would suggest fields or car parks or land of this nature. So once you're happy with the polygon, you can either double click to finish it, or you can click back on the beginning point that I added. Once that's done, you can also move the polygon around if you need to. You can edit the location of the points and you can add new ones, and so on. Once we've drawn the polygon, the tool calculates for you how much land that corresponds to. So in this case, about 16,000 meters squared. If you happen to already know what the land available is, and you don't need to be outlining it on the map, then you can delete the polygon, or let's just pretend that we started from scratch again, so we have the pin. You can input it directly into this field. So if we do input a land available for boreholes, then the tool will calculate how much of the heat demand of the site that can be met by boreholes covering this amount of land area. Finally, the last thing to mention on this page is this borehole depth option. So we've got a drop down here where you can choose either 200 meters or 100 meters, and these are two common options for the depth of boreholes. What you choose here affects the cost of drilling the boreholes, so the capex costs that the tool will output, but also how much heat that can be extracted from the boreholes. So of course you can extract more heat from a 200 meter borehole than you can from a 100 meter. In this case, I'll leave it as 200 meters. Once that's complete, then you can move on to the next step. And we have a screen here which allows us to add information inputs for up to 10 buildings. In this demo, I'm going to add 2 buildings. And for the first building, we have the building reference. Again, this is just a name for your own information or reference. Second, we have a build date of the building. The building sector, in this case, education, which presents us with another list where we can select a more detailed building usage category. These types of fields are used to estimate the site's heat demands and what could happen to those heat demands if we were to apply fabric retrofit to the building. But I'm getting ahead a little bit of myself, but just keep that in mind. So next down we have the internal area of the building. I've roughly measured this again in Google Maps for the building we're looking at, and I think it's got about 3,000 meters squared internal area, including all of the floors. The building perimeter is about 250 meters. It's got 2 floors, and the height between the floors is 2.4 meters. Again, these types of information are used to estimate the heat demands of the building and what might happen if we retrofit the building. Next, we have information about the current state of the heating system and its demands. So I'm going to assume this building currently has a gas boiler, and we have space here to input measured data, essentially. So the annual fuel demand, gas demand in this case, and the peak fuel consumption. These fields are optional. If we don't input these, then the tool will go away and use what we have input before to estimate these values. However, we strongly recommend that you do input these where known, because it's likely to make the results of the tool much more accurate. For this building, I'm just going to leave them empty. We then have this equivalent full load hours field. And if you've not heard about this measure before, it's essentially a measure of how hard you're working your heating system. In the information pop-up here, we suggest that if you have a building that's used during the day only, like an office, or in this case, like a school, then to use the value 1,800. If it's a building that's occupied and needs heating for 24 hours of the day, like a hospital ward, then you can use the 2,400 option. So for this school building, I'm just going to use 1,800. And finally, for this building, we have inputs for the current fabric of the building and whether we want to upgrade any elements. So here I'm going to assume we have a flat roof, we have double glazing, and I'll say cavity walls. For this building, I'll leave these all as no upgrade. So that's to the roof, the glazing, and the wall. And when I'm happy with this building, I can confirm the building. I'm going to add a second building, so I'll go through this a little bit faster, but just to show you the functionality, the full functionality. So I'm going to give it a generic name. I'll say it's built a little bit earlier than the previous building, and I'm still assuming that this is a primary school. This one is going to be a little bit smaller. The current heating system, I'll input gas boiler again. In this case, I will input these values for the current heating system's demands. So I'll say we have an annual demand of 150 megawatt hours and a peak gas demand of 180 kilowatts. And yes, we have options to choose different units if the default is not what you already have measured in. So for equivalent full load hours, I'll again go for 1,800. And in this building, I'm going to actually apply some upgrades to the fabric. So for the current fabric, I'm going to say it's got a flat roof type, single glazed windows and solid walls. And I will upgrade each of these components. So I'll upgrade the roof, upgrade the windows. We have different types of windows here, and this influences the cost of the window retrofit. And I will also upgrade the wall, so apply insulation to the walls. So once we're happy with our building data information, we'll go on to get our results. So it only takes a couple of seconds, and the tool has in the background ingested all your inputs and calculated these that we'll go through now. So first of all, what we see is that this high level result that 87% of your annual heat demand could be delivered by the ground source heat pump. Of course, these results are all indicative, and you should consult further professional advice for a more detailed assessment. But hopefully this is a good starting point to tell you how feasible a ground source heat pump could be. So there is this unique code that's presented to you. This is what you would use to retrieve your results in the future if you want to come back to the tool, and also gives you the ability to edit your inputs in the future. It sort of saves your inputs. I'll show you that functionality later on. So scrolling down, we have this navigation menu on the left. First of all, in the navigation menu, we have the inputs that you've put into the tool, and this is just, to give you the opportunity to double check these things. So we have the site details that you've input, as well as all of the inputs that you provided for each of the buildings. So we have the two buildings here. And then we come on to the more detailed outputs. First of all, we have information about the geology of the site. And like I said earlier, it's got this information from a database in the tool, and it's all based on that what 3 words input that you provided. So we have an indication of the predominant geology in the site. In this case, we have river terrace deposits, which is unsurprising given we're quite close to the River Severn in this demo. And the dominant bedrock is this type. We then have a planning prognosis. So in this area, we don't think that you need to contact the Mining Remediation Authority for any planning purposes if you were to go ahead and install a ground source heat pump. However, there may be natural England designated areas nearby. However, there are no source protection zones present. We then have the drilling prognosis. So we don't think that underground coal mining has been happening in this area. We then have an indication of the minimum casing length of the boreholes that would be required, and we think that would be up to about 15 meters. Then we have the power prognosis per borehole. So at 200-meter depth of borehole, which we input, we think you can get 8.3 kilowatts of power from each borehole, and that's assuming 10 meters of borehole spacing. And then we have an approximate number of boreholes to meet the demand, either to meet the full demand or to the maximum that you can install in that land footprint of 1,000 meters squared that I input before. So in this case, the approximate number of boreholes has come out as 10. Again, assuming 10 meters of minimum separation. So we then have some ancillary information here, indicating how easy it may be to trench on site for the piping between the ground source heat pump boreholes and the building itself. And then an indication of the alternative geothermal options that you could be considering. So similar to before, we don't have any coal mine heat information for this area. However, we think that open loop ground source heat pump is favourable for this area. So the percentage here refers to the percentage of the hex cell that your site sits in. The hex cell is something that's in the background of the tool. So it's looking likely that you could be using an open loop ground source heat pump here. However, the rest of the results are only referring to closed loop ground source heat pumps. Finally here, deep geothermal heat resources might be available in this area, so that's something to consider. Now we come on to more numerical outputs of the tool. So first of all, we have site demands. And this gives you the view of what the tool has calculated for your total site demands, both in the current world where you've got the current fabric of the building and in the retrofitted world where, in this case, I had applied those retrofit options to the roof, to the windows and the wall for the second building. So all of these outputs from now on are at site level. We don't go down to building level. These graphs are showing the annual heat demand in kilowatt hours and the peak heat demand in kilowatts for the site. We have the current fabric and the retrofit fabric results. So of course the heat demands all go down with the retrofit fabric world. And what we're also showing is how much heat is delivered by the ground source heat pump and how much is beyond the capacity of the ground source heat pump. So in the world where we have the current fabric still, for example, 84% of the heat can be delivered on an annual basis by the ground source heat pump, and 16% is beyond the capacity of the ground source heat pump. In this case, that 16% means about 60,000 kilowatt hours of heat. And similarly, we see similar results for the peak heat demand. Of course, the peak heat demand is calculated for the kind of coldest day in winter. So, you know, the ground source heat pump is working very hard, but the heat demand is higher. So more heat from a capacity point of view on the coldest day needs to be sourced from something other than the ground source heat pump. What we have in the tables are largely the same results that we have in the graphs, but now just tabulated. Perhaps you'll find these easier to share these numbers or to look at these numbers, so I've just included them in table format as well. So current fabric and retrofit results in 2 columns here. Total site demand, total site peak demand exactly as shown in the graphs, as well as the percentages that could be delivered by the ground source heat pump. What's a little bit new here that's not in the graphs are this ground source heat pump capacity value. So the tool has seen that for your location and for the amount of land that you have available, and therefore how many boreholes you can fit into that land, we can get about 120 kilowatts of heat from those boreholes. And finally, the last row here is an indication of how much electricity consumption that your ground source heat pump system would be using annually. Next, we come on to the costs and carbon section. First of all, we have the results summary, and then we have the results breakdown. So I'll start with a summary. What I will note here is that we actually have two options, the two tabs here, that show quite similar things. However, the difference between them is what top-up heating system is being used to cover this portion of the heat demands that is beyond the ground source heat pump's capacity. So, for example, in the first tab here, we have the ground source heat pump, which is using a top-up of the existing heating system type. In this case, that would be the gas boiler. But if you'd selected biomass boiler, then this would be representing a ground source heat pump with a biomass boiler top-up. The second tab is showing similar results. However, the top-up system here is actually an air source heat pump. So that's the difference between these two tabs. It's what the top-up heating system is. Aside from that, the layout and what you'll see in the results is quite similar. The first graph that we have here is the site level 30-year cost. We're showing 30-year costs because this is the rough lifetime of each of these heating systems that we're talking about. And these costs contain CapEx for the heating systems, OpEx for the heating systems, energy costs, and for the ground source heat pump case, the costs for drilling the boreholes and the hedging of the boreholes. In the existing heating system case, we have included the replacement of the heating system, assuming that needs to happen once during the next 30 years. So in this case, we're assuming that your gas boiler for this site is replaced, and so we've got the CapEx cost included in this. We've also got the costs split between the current fabric and the costs with retrofit results. So these green bars include the costs of retrofitting, but also take into account the reduced cost of energy, for example, because you've got a more efficient building. So yeah, the existing heating system represents essentially what you've got right now. The air source heat pump is showing the costs and carbon, if we look at the below graph, for a full air source heat pump system. So that gives you a bit of a comparison point against the ground source heat pump options. And then the third bar here is showing the ground source heat pump plus the top-up heating from another system that is required. In this case, it's the gas boiler that's being used as the top-up system. The next graph down is similar, however, it's showing the carbon emissions over the 30 years. And we're seeing that the air source heat pump wins out here. It's higher in the ground source heat pump case because of the top-up coming from gas boilers. At the bottom of this page, we have, again, just tabulated the results that are being shown in the graphs. So there's nothing additional in these tables that are not shown in the graphs. If we go to the results breakdown page, we're presented with a full breakdown of where those figures that I was showing you come from. So first of all, we have the retrofit cost. And of course, in the world where we're looking at just the site with the current fabric, this is not applicable. But in the world where we do apply the retrofit, then we have this retrofit cost that applies. So that's the CapEx cost. First section, so this, I'll explain that. This table is broken down into 3 sections. The sections are representing the different heating systems here as they are in the graph. So first of all, we have the existing heating system. So as I said earlier, we're suggesting that the gas boiler in this case will need to be replaced once during the next 30 years. So we've included the capex cost of that. It's less in the retrofit case because the peak heat demands come down a little bit. We've got the OPEX for the gas boiler in pounds per year, and we have the gas costs again in pounds per year, so about £10,000 to £12,000 per year average in this case. The cost assumptions for energy and also the carbon assumptions for energy are coming from the Treasury Green Book. And then we also have the carbon emissions for the gas annually. Next, we have a very similar split of costs and carbon for the full air source heat pump system. And finally, the same thing for the ground source heat pump, in this case with the existing heating system being used as a top-up. So here we have more rows because we've split things out into the ground source heat pump portion and the gas boiler portion. So the only additional thing here is that we've included also the borehole drilling and headering costs for the ground source heat pump part. But the other rows we are showing the same thing: capex, opex, energy cost, and carbon for each portion. So that's the results breakdown page. I'll briefly show you what the same thing looks like, but now considering a different top-up system. In this case, we're looking at air source heat pump top-up rather than gas boiler. And we have a very similar set of pages and results. The carbon emissions here, for example, are lower than the air source heat pump, so that's one obvious difference from the last set of results that we looked at. And the breakdown here shows the same thing for the first sort of half of the page. We have the retrofit costs, costs for existing heating system, and the full air source heat pump system. Nothing will have changed here. What has changed is the breakdown when we look at the ground source heat pump plus top-up part, because now the capex and opex, etc., of the top-up heating system is of course the air source heat pump option rather than gas boiler. The last tab that we have here is the further guidance and next steps. So if you've seen favourable results and you're interested in continuing the feasibility study, you can see in the tool guidance that I showed you earlier, you can find some next steps here that will help you along the journey. One thing I will show you here is we have an ability to edit your inputs very quickly. And there's one particular thing I would like to show is if I increase the land available for boreholes, this is, I don't need it to be this large for my site, but I'll show you what is going to happen here. And if I go back to get my results, so everything is recalculated here. So now we have 100% of the annual heat demand can be delivered by ground source heat pump. And one change that we see in the layout here is that the costs and CO2 section has changed. So we don't have the view of what the ground source heat pump costs and carbon look like with the top-up heating system, because a top-up heating system is no longer required. So the costs and carbon, both in the summary and the breakdown, only relate to the full ground source heat pump system. We have the option here to print results to PDF. So this is an easy way to save your results for future reference. And everything that I've shown in the results page gets printed out here. And finally, what I would like to show you is the functionality to return to your inputs easily in the future. So by copying this unique code, I can, let's pretend that I'm coming back to this in a few weeks' time. If you have saved a note of that code, or you can find it in that printed PDF if you've also saved that, then you can copy and paste it into here. And we come back to the inputs pages, starting with the site and location data. Everything is pre-populated. And if we would like to view the same results, we can just continue to get results. If we would like it to make a change to any of these inputs, we can make that change. and view the new set of results. So that brings us to the end of this video demo. I hope this has been insightful and that you find the tool useful.